All right, calculus students. This recording is not from 2020. This recording is from now, 2022. Because I can't seem to find this next lesson in my channel. So I'm forced to have to do it again. Maybe I have it a different name. But where are we at? By now, you should have already worked on your properties of definite integrals, and you should have worked on rectilinear motion. You should have worked on accumulation. That's the definite integral as we accumulate it. It's applications of the integral. And now we are going to work on the average value of a function. The average value of a function. So a function on an xy plane may look like it has a max, it has a high, and somewhere between this max and maybe I better put a min to this thing here. Well, I don't have to put a min. I can say from A to B, what is the average value? In other words, what y value would be the average value. I'll call it y bar. It's an average value. And it's used with integration because as you change this function, as x changes, y is changing, it's a lot of changing going on. So let's go ahead and let's attack the average value of a function. Most people just think of it as a formula, but it does have a concept with it as well. I believe this is going to be day 28. Day 28, I wish. Day 58 of lessons. And how have we found average velocity? Well, the average velocity came from, let's see, if we only had one endpoint and another endpoint, and we don't know what was going on with this function. This function could have been doing all kinds of stuff, But we wanted to find the average velocity. It was the slope of that line that went through x equals to a and x equals to b. So average velocity was f of b minus f of a divided by b minus a. It was the average slope. What would have been average acceleration? Well, for velocity, we use the position. I call it f, I call it s, whatever I want. So average acceleration would have been your velocity of b minus velocity of a over b minus a. In this case, I could have said f prime of b minus f prime of a over b minus a. That is average acceleration, because I'm using the velocities. For average velocity, I'm using the positions. So that was nothing new. But look at what's happening here. This is the average value function formula. 1 over b minus a looks very familiar to this 1 over b minus a. But look what's in here. You are integrating from a to b In other words, you are breaking the acceleration function into tiny, tiny rectangle areas again. And so instead of saying one large secant line, you actually have this fun. We would zoom in on that piece. You're actually doing a microscopic secant line from here, then another secant line from here, another secant line from here, another secant line. You get the idea? You're breaking it up into infinitesimally small secant lines. So we're accumulating the slopes, basically, of different pieces here from A to B. So when I do the integral of the acceleration function, then this turns into 1 over b minus a times, well, when I integrate acceleration, it knocks it down to velocity. Velocity of b minus velocity of a. What did I just do? This was the average value of acceleration function. Now I have, again, I'm breaking it apart. The slope, f of b minus f of a, all divided by b minus a. But again, whether it's acceleration function or whether I'm looking at the velocity function, I am still, if you zoom in, you'll see that I have an endpoint, and that would be, in this case, v of a, and then this was v of b. So still I'm dividing it by b minus a, but there's a whole bunch of them, okay? That's the concept of what's happening here. So when I integrate velocity, I get position. So I have 1 over b minus a, and I'll call position s this time. S of b minus s of a. And what this is the average value of the velocity function. The average value of a function, any function at all, doesn't matter whether it was the acceleration function, the velocity function, the average value of the temperature function, or the average value of the, what was the other application we had? We had temperature, we had water being poured into a swimming pool or taken out of a swimming pool. Either way, it's always going to be 1 over b minus a times the integral from a to b of whatever function we are talking about. Now, some books write it as integral from a to b of f of x dx divided by b minus a. Same thing. So if I move on here, so memorize that formula for the average value of a function. Average value of a function. Memorize that formula. Up at the top was breaking it down into acceleration and velocity functions, but really it's not that important that you remember that. This is what's important, that you remember this formula. We're going to find the average value of this function. I don't know what this function even represents, okay? That's why it doesn't matter if it was acceleration or velocity. It's just a function. So the average value of the function, so average value of this function will be 1 over b minus a integral a to b of f of x dx. So setting it up with my, writing it in, I'm going to 1 over, and this would be my a and this would be my b. We go from left to right. So I'm going to put 3 minus 1, integrate 1 to 3 of x cubed square root of sine squared x dx. Now, again, this is not an integral that you can do by hand. So you're going to have to use your calculator to get the average value. And that gives me 1 over 2 times the integral of 1 to 3 of x cubed square root sine of x squared dx. I have to use my calculator, and I'm going to just key it in. In my 84, I key in math 9. I'm looking for the integral where I key in the limits, and if we need practice in the calculator, you got to yell out at me about the Inspire. I don't know how to use Inspire, but I know I've seen people find that function already. We already practiced it once. I'll be back. It turns into approximately 5.848 is the average value of that function. Okay. What's happening in this, and maybe in physics you've seen something like this. You have this crazy function from A to B. And I don't know what it's doing. It's doing some crazy stuff. And at A, I'm here, and at B, I'm here. What we've really basically have done is we've tried squishing this area from A to B. We're really squishing it into a rectangle. We're squishing it into a rectangle by kind of like, imagine pushing this function down and like Play-Doh and get all the area. And what happens is this value here is your average value. Whatever this y value is, it's your average value. This is my rectangle with the length of b minus a. And how high am I going? I'm going to, that's my length or my height, whatever that y prime is. That's actually the integral. I'm sorry, well, anyway, that's my, I'm squishing it into this rectangle. If I knew how high this was, I'll just make it up, like C, and this is K, then the area under this curve, the black part, is exactly the area from A to B of this f of x, the average value, would be actually the same as this rectangle. B minus a times the antiderivative that we were talked about. So what happens is, if I divide both sides by b minus a, boom, that you get this relationship. It's related, even though the author didn't bring it up. Let's do another problem. Find this one looks like we could probably integrate. Find the average value. I'll call it average value is going to be the integral. Well, I need my 1 over b minus a. This time it's 6 minus 2. That's 4. 1/4 times the integral of from 2 to 6 of 2 minus 4x dx. This one says non-calculator. This one said calculator. Makes sense. Calculators, I couldn't do it anyway by hand. Non-calculators, I can do this. This equals 2. A constant 2 becomes a 2x. X becomes an x squared. Divide by 2. From 2 to 6, but don't forget, the whole thing was being divided by 4. So I'm going to keep that. I could have put 1/4 in front. It doesn't really matter. If that makes you happier, then I could go all of that times 1/4. It works for me. So I'll keep it that one. 1/4 of what? Be careful here. I got to plug in the 6 first. So that's 2 times 6 is 12 minus. That's 4 divided by 2 is a 2, so it's 2x squared. Plugging in the 6, so it's going to be 2 times 6 squared, because 4 divided by 2 is 2. This, be careful here, that's when I put in the upper limit, minus, now I'm going to plug in the lower limit, plugging in the 2. 2 times 2 is 4, minus this, remember this became a 2x squared, so that's 2 times 2 squared. And all of that was times the 1/4, so let me plug it all in. 1/4 of 12 minus 12 is 0. No, I'm sorry, it's not 12. That's 6 squared. Silly me. That's 12 minus 36 times 2. 72 minus. And then 2 times 2 times 2 is 8. 4 minus 8 is a negative 4. So I have 1/4 of all of this, which turns into 1/4 of 12 minus 2 is a negative 60. Minus minus is a plus 4. So I hope the average value is approximately a negative 60 over 4, which would be a negative 15. And, oh, I did my math wrong. Negative 60 plus 4 is a negative 56. Hello. Pay attention, Cartwright page. Negative 56 divided by 4, that's not that. Well, I'll put equals now. I can say 26, 13. Yeah, negative 14 would be the answer. Sorry, 14. So average value of a function. Piece of cake, right? Whoop, whoop. Another page. Okay, so what we got here. A ski resort uses a snow machine to control the snow level of a ski slope. Over a 24 period, the volume of snow added to the slope per hour is modeled by this equation. So that is the amount of snow, is what it says. The amount of snow, the volume of snow. Okay, so every hour there's more snow. They're measuring it by volume, okay, which would be cubic units. In this case, I don't see the rate which the snow is modeled. Well, no, that's not the right one. I'm still on S. The volume of snow is volume of snow. I don't see the unit just yet. Well, I'll keep reading here. Whatever, it's going to be cubic units. The rate at which the snow melts is modeled by this equation. Oh, so we've got snow being added and we got snow being melted. It's two functions working together simultaneously. And neither of those functions can you integrate by hand. I'm just letting you know, I can tell because I've not taught you how to handle an argument that is not just a t. But anyway, both S and M have units of, there it is, yards per hour. Okay, so we have two rates competing with each other. And t is measured in hours for the interval from 0 to 24. So there's a day. It's a whole day. We know that at time t is 0, so when we started the clock, they already knew there was 50 cubic yards of snow. So we're starting out with 50. Then the clock goes and snow is coming and slow is being removed. And, it's coming because of, how are they doing it? With a snowplow to control the snow level. So the snowplow is building up where they need the snow, and then the temperature is causing snow to melt. So compute the total volume of snow added to the mountain over the first 6 hours. We're just talking about being added. So we're using accumulation of snow. We're accumulating the rate of snow. We're integrating the rate of snow being added with the snowplow. That would be the integral. So the volume of snow that we're looking for, the total volume of snow at this point would be the integral 0 to 6, first 6th period, of just S of t, which is 24 plus a t sine. Yeah, that'd be a harder function to work on. Can't get my t sine of, I think something's missing there. I think they missed the variable of another t. I'm going to have faith that there's supposed to be another t here. Sine, oh no, the t's inside, t over 14. And that trig function is being squared. So I put that there, put the squared there, dt. Can't really do this by hand. So you need to go to a calculator and integrate that function from 0 to 6. And I'm going to go do it. And I'll come back to you and we'll see what the answer is. I hope you guys are typing these things in first. I hope you're pausing the video and then doing it yourself to make sure you can do it. If all you're doing is copying my work, it's going to be very easy to know that you never did it with a calculator. I will probably find out within this week for sure. All right, anyway, enough on my soapbox. 142.413 cubic yards. 14241. That was pretty easy. Find the value of 0 to 6 of the melting snow and 1/6 of the melting snow. Wonder why we're doing 1 out of 6. I'm looking at my limits. A to B, and B minus A would be 6 minus 0. This is the average value. This is the accumulation of melted snow. Use correct units of measure and confirm what each represents. Well, I just told you. I didn't know they were going to ask that. But with my calculator, I know that the volume of melted snow, I should put melted, this was volume of snow being added with the snowplow. This is the first one in 6 hours. And the function for this one was, melting was 10 plus 8 cosine of t over 3. 10 plus 8 cosine of t over 3 dt. So I'm going to do that with my calculator and get an answer. Then I'm going to do my average value of melted snow. That's going to be 1 over b minus a, which is 1 over 6. Integrate 0 to 6 of this. It's the same formula. 10 plus 8 sine of t over 3 dt. Actually, you're going to realize that the average value, since the melting snow changes as the function changes, must be less than the total volume of melted snow. Because you're going to have this function, which here's my melting snow function, melts a lot, melts a little more, melts a lot, whatever the case is. And if you're going from 0 to 6, we're talking about this box here, and we're talking about pushing the average down below it. So the accumulation from 0 to 6, this average value right here, this line that is the average of the amount of melting snow. Since the function changes, it's hard to average up dots that are changing. So go to my calculator and I'll be right back. I'm going to get the first answer, then I'll come back and get the second answer. you should be pausing and do it yourself. Approximately 13.367 yards cube, or cubic yards, or yards cube, however you want to do it, of snow. This means the average rate of melting snow from t is 0 to t is 6 was 13.367 yards cubic yards. And it is less because, be interesting to check that rectangle and that height that the volume got pushed down into is to 13.367, and from A to B was 6. Be interesting to calculate that answer. I just did the math for you, if you can see where it just appeared up here. I did the area of this rectangle. And the only reason why it's not exactly the 81.823 is probably because of rounding of that number. So it's still the same amount of snow, but the average per time is at 13. Because, face it, the function changed a lot, up and down, but the average amount of snow per unit of time, whether it's a second or a minute or an hour or whatever you want to call it, was still 13. We're talking about in that six hours of thinking. C, is the volume of snow increasing or decreasing at time t is 4? Well, to talk about increasing or decreasing, don't I need the derivative? Wouldn't I have to know what was going on at 4? Wouldn't I need to talk about the snow that's coming and the snow that's leaving? Accidentally hit mute. Isn't the volume of snow that's increasing or decreasing needing a derivative? So I need to have my amount of snow equation. The amount of snow equation should be let's see, I started out with, let me go back up. You got to always have your initial. So we started out with 50 yards. So we start out with 50. Then I added snow from the S of t. And that was going from 0 to 5. That's the first 5 hours. But then I have to take away the snow that is melted. 0 to 5 of the m of t. So I need to know if this is at 5. Doing the derivative straight across, a prime of t, derivative of a constant is 0. That goes to 0. When I integrate this integral, out pops out the integral, and I'm left with s of t. And since t is becoming a 5, it's going to be 0 plus s of 5 minus, and also this becomes m of t, but because I'm taking the derivative straight across, derivative cancels out the integral, and I'm going to be plugging in 5 in place of time, so that's going to be m of 5 is going to be some value that I need to know if it's positive or negative, because positive means it'd be increasing, negative would imply it was decreasing. I'm not going to rewrite S of t and M of t equation. I'm going to use these two equations and I'm going to plug them in my calculator, not the 1/6, but just the M. Well, I better put them up here. I'm going to plug in the S equation. I'm going to do the 50 plus this equation at 5 and plus this equation at 5 with my calculator. And come up with an approximation number. Be right back. 95.3. Is it 3? I forgot. I coughed. I forgot. Is it 335 cubic yards? Let me go back and look at my calculator. Yes, it is. That's the total amount of snow on the mountain after the first 5 hours. Oh, snow came, snow left. Started out with 50. Suppose the snow machine is turned off. I did it again. At time t is 10. Write, but do not solve an equation that could be used to solve time t is k, when the snow would all be melted. Well, we first need to find out how much snow is on the mountain at the 10th hour. Because the machine was working, and snow was melting, and so we do have a value of snow after the 10th hour. Then the machine's going to stop. So allow me to say, well, I started with 50 yards of snow, cubic yards of snow. And then I'm going to have plus 0 to 10 of the S of t dt. That's the snow being plowed in and, being made and all that. There was still snow being melted. 0 to 10 of M of t dt. And the shortcut that I'm doing about naming these functions is legal. You do not have to rewrite all those fancy equations as long as somewhere you made note of M and S equations. So probably I would write it one time and write S of t is boom. M of t is boom. That way you could always refer to those instead of actually writing them on your test paper. I mean, bottom line, I'm going to put them in my calculator. I have it in the calculator. I have the S and the M equations, Y1 and Y2. And I'm just referring to it when I need them. That way I don't have to keep typing in my calculator either. Anyway, so this is not going to take me long at all because I already have these equations and I've already did the 0 to 5 or 0 to 4. I'm just going to change that upper limit to be a 10. And I'm going to get one answer to how much snow am I starting out with. So pause it or wait for me to come back. $193.183 yards cube of snow. Assuming I saw my numbers right on my calculator. 193. See, I can't look at it right now because it's on the program that I use, and when I go to that program, my recording stops. I'm going to double check it because I don't have faith, and nobody's there to tell me 183. Let me look. Well, it's not. I just looked at my calculator. It's 193 cubic yards. Sure pays to have somebody in here. Okay. Now that's how much snow is on the mountain right now. And I need to melt it all. So what I'm going to have to do is start out with that much snow. 193 point. Wait, is that the right answer still? I might still be off. 193.193. Let me look. I'm going crazy. No, it's 183.193. I just erased it. 183.193. Okay. Better for me to find it than for someone to write me a message and tell me I'm batty. So I'm going to start out with 183.193 cubic yards, and I'm going to subtract the melting snow from, well, I know it's melting from 10 to something, 10 to K. K is the time that I don't know. You know, it's got to be within that 24 period. Okay, let me look at my... So, well, I don't have to solve it. You can solve it. There is a way to solve this problem for K, because bottom line is I want this answer to be 0. So there is a way to find K, but we don't have to. He just says do not solve it. The good news is a lot of times the AP exam, they don't really care about all the technical work. They already tested you a lot on using your calculator and doing a lot of integrals. This lesson is very, very important, guys. These last 2 lessons are probably worth up to 20% of your AP test. The concepts that are embedded in them. If I were you, I would do these lessons twice. Do the homework so that you truly understand it. And you'll be good to go. What's after this? Well, an AP problem. And I have not hid them from you. I've given you exactly the year that this problem came out, and what problem it is. You can find the solutions. I would suggest that you do this problem first and be as careful as you can be on details. It's better to write more than you need, as long as it's accurate. Then go and look at what the grader said you had to have to get 9 points for this problem. And if you can figure out that when you look at the rubric, if you can justify 4 to 5 points, you are on your way to gold. That means you know your stuff enough to get a 3, 4, or 5 on the AP test. So there's one problem there for you. And then there's another problem using a table. The first one was a graph. That was a table. And then there's your homework. So I would use those problems. I really would use class time to get those, work with your neighbors on those free response. And now you're going to work hard on this one. And after this, day 58 homework, day 59 is actually starting here. 1 free response, 2 free response, 3 free response. These are all release problems, guys. It's your 3rd one. That's day 59. We're done with Unit 6. Unit test is coming. Get this stuff done this week. Over and out.